Hello. So today we're going to start Unit 3. We're going to talk about topic 3.1, which is chain rule. And to begin Unit 3, we're going to talk about functions that we can already take the derivatives of, and some things that are a little bit more complicated that we're going to learn how to differentiate today. So the table that I have at the very top here is all stuff from Unit 2, right? So we have a quadratic here we can use power rule on, derivative of sine. So we have our basic trig functions. We can even use our sum and difference rules, product rule, quotient rules in the table, but we all know how to do that. The problem comes is when we start to have a composition of functions. So if you compare it to the right column, if I were to take that same quadratic and I put it under a radical, okay? To take the derivative of that, we have to apply something called chain rule, and that's what we're going to learn about today. So, same thing with sine. If I put instead of x, I put a 6x. So I put an expression inside of sine. Or if you look at the second one, I squared sine, right? So the derivative of sine squared is not cosine squared. So we have to be very, very careful with that. So what we're going to learn today is how to take the derivative of a composition of functions. And I kind of have some notation for you to look at. So little sentence at the top, I want you to be able to read the mathematics. So if y equals f of u is a differentiable function and u equals g of x is a differentiable function of x, then y equals f of g of x is a differentiable function. So if the outer function is differentiable and the inner function is differentiable, then you know that the composition itself has to be differentiable. And also a reminder, if it's differentiable, we know that it's continuous. Okay, but take a look. So this is what we want to pay attention to here. If you were to take a look at this first expression, if I take the derivative, okay, of f of u, right? I'm going to take the derivative of f prime, and the inside stays the same. Notice it's just u, okay? But then we need to multiply by the derivative of the inside. So that's this du dx, okay? So what we're going to do is we're going to get this extra little product, okay? So equivalently, if you take a look at this, I'm going to work from the outside in. So if I have f of g of x, well, now I'm going to take the derivative of f, right? I leave the inside the same. I don't take the derivative of anything on the inside of that function, and then I'm going to multiply it by the derivative of the inside. That's what chain rule applies to. So what I wanted to do is I want to start with just function notation. I didn't want to overwhelm with all the different function derivatives that we know. I just want to take a practice with just the function notation. So if you look at example 1, we have a few different problems here. I want to know the derivative of these functions. So I'm going to say, okay, h prime of x is going to equal. Now I want to look at what the outermost operation is, and that outermost operation is a 2, okay? Is that power of 2, I should say. So what we're going to do is we're going to apply power rule. We're going to drop the 2 down. We're going to leave the inside of that operation the same, and it's now to the first, right? Because we have to lower it a degree. So all I did was apply power rule. But now I want to take the derivative of the inside. So that's where my product comes into play. So now I'm going to multiply by the derivative of the inside, okay? So my answer, or my derivative, just to make it look nice, is going to equal 2 f of x to the first is just f of x times f prime of x, okay? And that would be my derivative, all right? So we're going to do this over and over. We're going to do it multiple times, all right? There'll be some practice built in. But take a look at b. All right, same idea. So I have a y, so the derivative, you can either do y prime or dy dx. Make sure we use good notation. I'm going to start the outermost function here, okay, is going to be the j. That's the outer piece. So I'm going to say j prime. Leave the inside the same. But then I want to multiply it by the derivative of the inside. And the way I express the derivative of m is just m prime of x. So let's write this out. So I have a dy dx equals a j prime of m of x times m prime of x. All right? And that would be my final answer. All right? Working from the outside in, kind of like peeling back the layers. All right, so let's take a look at C. We're just going to keep going. Okay, feel free to pause the video, rewind, okay, whatever you need. So again, I start with y. So we're going to do a dy dx. Okay, I'm going to start with the outer function, which is f prime of, leave the inside the same. But then we want to multiply by the derivative of the inside. And the derivative of x squared is 2x. The derivative of 5 is 0 because the derivative of any constant is 0. So let's start to clean this up a little bit. dy dx equals f prime of x squared minus 5 times 2x. And there's a good chance if you were on a AP test or multiple choice, dy, let me make that look nice and neat. They would put that dx in front. So if I have dy over dx equals, they might write it like this, 2x times f prime of x squared minus 5. Okay, and this is my derivative. Okay, let's keep going. I have f of x, so I'm now going to have an f prime of x equals. Start with the outer function, that's g. So I'm going to say g prime. Leave the inside the same. Okay. Now I want to multiply by, take the derivative of the inside, which will give me 2h prime of x. Now we didn't need to do a product rule or anything like that because the 2 is just a constant multiplier. Okay. So we didn't have to do anything fancy. Derivative of h is just h prime. So I'm going to write this nice and neat. F prime of x. I don't think there's too much to clean up here. 2h of x times, yeah, there's really nothing to clean up here. 2h prime of x. And this would be my derivative. Okay? So let's see if we can put that into practice here. All right. I'm gonna do now some problems that have multiple links to the chain. Sometimes we have a composition of 2, 3, 4 functions, and we need to kind of follow that process. So I kind of made a few examples. We'll go through them slow. All right. I have f of x, so I'm going to have an f prime of x. And we're going to start from the outside and work our way in. So the derivative of g would be g prime. And we're going to leave the inside exactly how it's written. So I have g prime of h of j of x. Okay? But then I need to multiply by the derivative of the next piece, which would be an h prime. But if you notice, the inside of h is still j of x. But then I still need to take the derivative of j, which would be j prime of x. So if I want you to see here, I took the derivative of g, I left the inside of g the same, but then I had to take the derivative of h, and then I left the inside of h the same, and then I took the derivative of j, and I left the x the same. Okay, and my answer here, so f prime of x is equal g prime of h of j of x, make sure all your parentheses are good here, times h prime of j of x times j prime of x. And this would be my answer. Okay, So we're going to do that a few times. You can see I have 4 examples here. So let's do it again. F prime of x is equal to derivative of the outside, keep the inside, the same. Then we're going to take the derivative, I'm using my red pen here, of the inside. So what's the derivative of h? Well, that's h prime. Leave the inside of h the same. But then I need to take the derivative of 5x, which is just 5. So my derivative here, if I write this nice and neat, I'm going to bring the 5 all the way, oops, didn't mean to write a 5 there. I'm going to bring that 5 all the way in front times g prime of h, excuse me here, let's try this again. Okay, there we go. Of 5x times h prime of 5x. And this would be my derivative. Okay, hopefully you're picking it up, but we got a lot of practice here. All right, so let's use the y prime notation today. So a derivative of y is y prime. Now I'm going to write this as f of 5x to the 1/2 power. Okay, so that's the same thing as a radical. So we're going to drop that power in front. That's the outer piece. Leave the inside the same. But when we drop that 1/2, we have to lower it a degree. But now we're going to take the derivative of the inside, which the derivative of f is f prime. Oops, f prime of 5x, right? Let's try that one more time. Okay, f prime of 5x. But then we have to take the derivative of the inside. Derivative of 5x is just 5. So if I write my answer, now we're going to try to write this nice and neat. All right. I would write my answer as the following. And actually, I'm going to give myself a little bit more room. I'm going to say 5 f prime of 5x is all on the top, and then I have a 2 times the square root of f times 5x, or f of 5x. Now the reasoning because of that is because I have a negative exponent, right? So if I have a negative exponent, we know that's going to be in the denominator. So I have this quotient here. All right. And that will give me my answer. Okay. We got one more. So let's do y prime. The derivative of natural log, remember, it's 1 over whatever's on the inside. So the derivative of natural log will just be 1 over f of 2x plus 1 times the derivative of my next piece, which would be f prime of 2x plus 1 times the derivative of my next piece is 2, which gives me a derivative of 2 f prime 2x plus 1 over an f of 2x plus 1. And this is my derivative. Okay? So let's talk about some numerical examples. We're going to do everything the same way. We're just going to apply some values to it. And for all of these problems, I want f prime of 5, right? So I want to plug 5 in for x. We're going to see what we get. Okay? So for part A, if I take the derivative, so f prime of x, let's get the derivative first. Okay, we're going to start on the outside. So the derivative of h is h prime. Leave the inside the same times the derivative of the inside, which would just be g prime of x. And now we're going to substitute in 5. So I want to know f prime of 5 will equal h prime of g of 5 times g prime of 5. All right, so now we have to find some values. We're going to do this step by step here. Okay, so f prime of 5, trying to keep my good notation, is going to be an h prime of, now g of 5. So if I look at my table, that's going to be 9 times g prime of 5, which is 6. So now f prime of 5 equals h prime of 9. So I got to look at my table of that. That's going to be 1 times 6, which just gives me 6 as my answer. Okay, so I'm taking the derivative just like I did before, but then I'm going to evaluate it using the values on my table. So if I do my next one for b, let's try to keep my colors going here. F prime of x is going to equal, now the outer piece of my function is that squared, so I need to use that power rule, 2 h of x to the first. You don't really need to write the 1 because to the first is just the itself. And then the derivative of the inside, which is h prime. So now I'm going to plug 5s in for all the x's. So h prime of 5 is going to equal 2 times h of 5 times h prime of 5. Okay. If I then start to evaluate this, I have an f prime of 5 equals 2. Now h of 5, if I look at h of 5, that's 5, times h prime of 5, which is a negative 4. So I'm going to get 10 times a negative 4, which is a negative 40. And that would be the slope of the tangent at 5, right? So we're finding the slope of the tangent at 5, or the instantaneous rate of change at 5. Okay? So next I have f prime of x. Now, we already talked about this radical. So this is to the 1/2 power. So if I do this, I'm going to get a 1/2. Inside stays the same to the negative 1/2 times a g prime of x. This is the derivative of the inside. So if I'm going to write this a little neater here. I'm going to call this g prime of x over 2 times the square root of g of x. Now I'm going to plug in 5. So f prime of 5 is going to equal a g prime of 5 divided by 2 square root g of 5, which let's find out what those values are. So g prime of 5 is 6 over 2 times the square root of g of 5, which is 9. That's convenient, right? It's a perfect square, which gives me a 6 over 2 times 3, which is 1. And that is the instantaneous rate of change at 5. Okay, let's keep going. Now, don't get freaked out with this 2 in front. That's a constant multiplier. But the reason I put D on here is I don't want you to forget your old material. D is not a chain rule. D is a product rule. Okay, you can do products for this. All right, there's no composition of functions here. All right, if I take f prime of x, I'm going to take the derivative of the first, which would be 2 g prime of x, keep the second, plus, now keep the first, and take the derivative of the second, and now I can find f prime of 5. So this was not a chain rule. I don't want you to assume everything's a chain rule. Oops, forgot I put my prime in the wrong place. Let's make that look nice and neat. Okay, g prime of 5, h of 5, plus 2 g of 5, h prime of 5. So let's figure out what those values are. So I'm going to have a 2, g prime of 5 is 6, and then h of 5 is h of 5 is 5, plus 2 g of 5. If I look at my table, I'm going to get 9, and then h prime of 5 is a negative 4. So I get 60, and it'll actually be minus, because I have a negative in there, minus, I believe, that's going to be 72, which gives me a negative 12 as my instantaneous rate of change. Okay? So 2 more. Now, part E, I'm going to do with a chain rule just so you can see how I can do it, but you can also do a quotient rule if you wanted. But I am going to write this as h to the negative 1 power of x, right? So this is just h to the negative 1. And actually, I don't want you to think it's an inverse, all right? So I'm going to write it as h of x, I'm going to use some big brackets, to the negative 1 power. So now I'm going to just use power rule with a little chain rule built into it. So drop the negative 1 times h of x to now the negative 2. But now I need to take the derivative of the inside, which would be h prime of x. So I'm going to get a negative 1 over h squared x times h prime of x. And you can put that in the numerator if you want. So if I want to find f prime of 5, it's going to be a negative 1 over h squared of 5 times h prime of 5, which equals, let's go to my table. So I need to know, I need to know h of 5, which was 5. So this is going to give me a negative 1. Now, if h of 5 was 5, then this denominator will end up being a 25, because I need to square it, times h prime of 5, which is negative 4, which will give me a 4 over 25 as the slope of the tangent. Okay? Last but not least, f prime of x equals g prime of h of x times h prime of x. So f prime of 5 is going to be g prime of h of 5 times h prime of 5. And so let's start. H of 5 is still 5. That's convenient. Okay, so if I do this, let's do one step at a time here. So h of 5 we said was 5 times h prime of 5, which I believe was negative 4. Yep. And then g prime of 5, because I'm doing that composition, is 6 times a negative 4, which is a negative 24. Okay? So now I'm going to steer away from the function notation. We're going to look at some of the common derivatives that we've looked at, right? Or that we've seen. So the first one was power rule, right? So we kind of talked about power rule already. We're going to drop the exponent, lower the degree. So if you look at some of these examples, so y prime here, if I drop the exponent, again, I'm looking at this 3 on the outside, the cubed. If I drop that exponent, we're leaving the inside the same. So that's going to be a 3x minus 2x squared still, now to the second power. But now we need to multiply by the derivative of the inside, which would be derivative of 3x is 3, and the derivative of a negative 2x squared would be a negative 4x. And this would be my derivative. Okay, so I take the derivative of the outer exponent, right? That's on the outside, times the derivative of the inside. All right, now for part B, I would actually rewrite this real quick to be an x squared minus 1. And it's squared to the, and a cube root is a 1/3 power. So a better way to write this to make it a little easier for us is going to be an x squared minus 1 to just the 2/3 power. That's a lot easier to take the derivative of. So if I do this, y prime, I'm going to drop the exponent down, x squared minus 1. Now, if I lower that a full degree, if you subtract 1 from that exponent, we'll now be at a negative 1/3 times a 2x. Okay? And that would be my derivative. Now, typically, AP does not leave negative exponents, so they would write it as 2 over 3 times the cube root of x squared minus 1 times 2x, and you can even put that 2x in the numerator, okay, to give you a 4x in the numerator. That would be appropriate too, okay? But there's my derivative. All right, last. All right, again, I would write this different. You can do a quotient rule if you want. You don't need to. Negative 7 times, I would write this as a 2x minus 3 to the negative 2 power. That's the same expression. So if I do a power rule, drop the negative 2 down, that gives me a positive 14. Keep the inside the same. But now if I lower degree, it'll be to a negative 3 power. Don't forget, times the derivative of the inside, which gives you 2. So my derivative, if I make this look nicer, is going to be a 28 over 2x minus 3 to the 3rd power. And that would be my derivative. Okay? So chain rule, derivative of the outside times the derivative of the inside. Okay? So that was just an explanation of power rule and chain rule, like connecting them. So let's take a look, same thing with our trig functions, right? So if you take a look now for part A, this should probably just read the sine of 2x, right? That's all inside of my sine. Same thing with part C. This is the secant of 4x. So I'm going to work from the outside in. So if I were to do these with a trig function, derivative of sine is cosine. Keep the inside the same times the derivative of the inside. And again, multiple choice would probably be a 2 cosine. Let's write legibly here. There we go. 2 cosine of 2x. All right. So for part B, y prime, derivative of cosine is a negative sine. Keep the inside the same times the derivative of the inside, which is just 3. Derivative of 3x is 3. Derivative of 1 is 0. Okay, so my y prime would be a negative 3 sine 3x minus 1. Okay, and that is the derivative. Last but not least, y prime derivative of secant is secant. Keep the inside the same. Tangent. Keep the inside the same. So whatever's inside the secant has to be inside both the secant and tangent. And then the derivative of 4x is 4. So I get my derivative. I'm going to bring that 4 as my coefficient. Secant of 4x times the tangent of 4x. And that is my answer. Okay. Now, same thing. So these just have more links to the chain. So there's just more derivatives that are products that we need to tack on to the end. So I have a y prime. Now, I want you to understand notation here. You see the sine to the 4th of 3x. This really reads sine of 3x to the 4th power. The 4 is really on the outside, and that plays a role because it tells us what order to take derivatives in. So I'm going to start with my power rule. So it's the 4 times sine of 3x to now the third times the derivative of sine, which is now cosine of 3x, times the derivative of 3x, which is 3. So if I write this and I put all my pieces together, I get a 12 sine cubed of 3x cosine of 3x. And that is my answer. All right. For part B, I'm going to write this as a secant of x over 2 to the 1/2. And actually, I'm going to do even one better. I'm going to say a secant of 1/2 x. No reason to think I need to use a quotient if I don't need to. So I'm going to start with the outer piece, which is the exponent. So y prime would be a 1/2. Keep the inside the same, secant of a 1/2 x. To now, if I lower the degree, that would be a negative 1/2 times the derivative of secant, which is secant of 1/2 x, tangent of 1/2 x. Now I have to take the derivative of 1/2 x, which is linear, so it's just a 1/2. So let's try to put the pieces together here. So y prime is going to equal a 1/4 secant of 1/2 x. I guess I don't really need that parentheses in front. Okay. Times secant of 1/2 x times a tangent of 1/2 x. Now, this is a square root here. We could actually combine these together. Actually, hold up. That was to a negative power, right? Let's go back a step. Okay. If this is still secant to a negative 1/2, okay, I can actually combine those two together because I have secant to the first and I have secant to the negative 1/2. So I would actually get a 1/4 square root of secant of 1/2 x times the tangent of 1/2 x. Because a negative 1/2 plus 1 is a positive 1/2, and anything to the positive 1/2 is a square root. All right, let's take a look at C. Again, I have the cotangent. Oops, I wrote cosine. Let's go back. I have the cotangent of 3x over 2. And I want you to understand when you have that power, that 2/3 is really on the outside here. So my derivative, I'm going to drop that 2/3 down, leave the cotangent the same. Everything inside this stays the same. But if I lower it degree, now I'll be to a negative 1/3 power times the derivative of cotangent, which is secant squared. Inside stays the same, so that 3x over 2 still stays 3x over 2 times the derivative of 3x over 2, which is just a 3 over 2. So my answer here, if I combine these coefficients, 2/3 and 3/2, is just a 1 cotangent of 3x over 2 to the negative 1/3 power secant squared of 3x over 2. And you could put that cotangent into the denominator because it's to a negative exponent. So again, I know these are a little complicated, but I want you to really, really focus on the chain rule, right? Starting with the outer operation, working your way in, all right? So if you take a look at this natural log, so we're just going to apply it to natural logs. So y prime, derivative of natural log is 1 over whatever the natural log is of. So in this case, derivative of natural log will be just 1 over 2x, right? The inside stays the same. We don't touch that. But now I need to multiply by the derivative of the inside, okay? So I'm going to get y prime to be a 2 over 2x, and if you reduce that, I get a 1 over x. All right, let's do that again. So derivative of y, natural log, I'm going to have a 1 over whatever the natural log is of, okay, times the derivative of the inside, which would be a 2x. All right, if I make that look a little nicer, I get 2x over x squared plus 1. And again, we can't really reduce that, so that's where we're stuck. Okay? All right, what about logs of a different base? Now, we'll talk about these log properties later, but what about logs of a different base? And actually, I want this not to be natural log. I want it to be of a different base. So let's say log base 5 of x cubed, right? So if I do this, now I purposely made this one here. If you notice, this is a product rule, x times log base 7 of sine of x. So we have to use a product rule. So derivative of the first, keep the second. Oops. Write that correctly. Log base 7 of sine of x plus, now I'm going to keep the first and take the derivative of the second. So the derivative of a log with a different base is going to be 1 over whatever the log is of, in this case sine, times the natural log of the base, which is 7. But now I need to take the derivative of the inner piece, which was sine, which gives me a cosine. So I get log base 7 of sine of x plus an x cosine of x all over sine of x ln of 7. I would not get common denominators. I would not combine those together. Okay, that would be my derivative. All right, let's take a look at b. Y prime. Drop the 3 down. So now this is squared times derivative of log base 5 of x would be 1 over the x times the natural log of 5. Okay, and this would be my derivative. Okay. We also did, in Unit 2, we did exponential functions. Okay, we did exponential functions. So derivative of e to the x is still e to the x, right? But what if it's not just x? What if it's an expression in the numerator? So if I have a dy over dx, right, derivative of y with respect to x, is equal to now e, it would be the same thing, right? E to the 2x cubed minus 3x. The only thing that we need to do now is we need to multiply this by the derivative of that exponent, which would be a 6x squared minus 3, and I just used my power rules, okay? And that's the derivative. I am going to write this next one, instead of e to the 1 over x, I'm going to write it as a -1, because it's just easier to do power rule that way. So a derivative of e to a power, right, is still, so dy dx is still e to that same power. We just need to multiply it by the derivative of that, so drop the -1 down, x to now the -2. So I'm going to write this a little better. And I'm going to say this is e to the 1 over x times a -1 over x squared, which maybe on multiple choice, they might write it as a negative e to the 1 over x all over x squared. And that is my answer. Okay. What about bases other than e? Now, we haven't covered this, so I'm going to cover it now. But if you look at the top here, the derivative of a to the x, so if you have a base that's different than e, we're just going to multiplying by that natural log of a. Okay, so that's kind of how this works. So the derivative of 2 to the x, okay, now there's no chain rule here. Okay, derivative of 2 to the x is just still 2 to the x. You just have to put an ln of 2 at the end of it, right? So if I do part B, okay, the derivative, so dy dx, derivative of 5 to a power is still 5 to that same power times the natural log of 5. Because that's the derivative of a base different than e. The only thing that we need to do now is we need to take the derivative of sine. So the derivative of sine is going to be cosine, right? And I'm going to write this a little neater here. So I'm going to say this is going to be the ln of 5, because that's a constant, times 5 sine of x times cosine of x. You can write that in any order. Multiplication is commutative. So that would be my answer. Okay. Now, what I'm going to do is I'm just going to take previous questions that we've had and I'm going to apply chain rule to them. So if you take a look at this example here, it says the graph of the function is shown at the right. The function h is defined by f of 2x squared minus x. Determine the slope of the line tangent to the graph of h. Okay, now the graph that I gave you is of f. I want to know the slope of the tangent of h. So again, I want to remind you, the derivative finds the slope of the tangent. So I want to know h prime. So derivative of f would be f prime, leave the inside the same, times the derivative of the inside, which would be a 4x minus 1. So now, to find the slope of the tangent line, I just need to know h prime of 1. So f of x equals, if I plug a negative 1 into here, I get 2 times 1, which is 2, plus 1, which is 3, times, if I plug a negative 1 into here, okay, I get a negative 4 minus 1, which is a negative 5. So if I look at my graph, I want to know h prime of 3. So I want to know the slope of that line at 3. Well, luckily, the slope of that line everywhere is the same. It's constant. So I need to try to figure out, okay, what the slope of this line is. And if you look, this is down to 1, 2, 3, 4, right? Or you could have even done down 1 over 2. The slope of this line is a negative 1/2 times a negative 5, which gives me a 5 over 2 as the slope of the tangent for h. Okay? So let's go back to those tables. Same idea. Now notice, for part A, write the equation of the tangent line to h when x is 2. So for the tangent line, we need a point and we need a slope. Okay? So the point, all right, is going to be 2 comma something. So I need to figure out what h of 2 is, which means I want to do f of g of 2, which would then be f. Now g of 2, if I go to my table here, g of 2 is 3. So then f of 3 is also 3. So I know my point is 2 comma 3. Now I just need to find the derivative for my slope. So I'm going to find h prime of x first, which derivative of the outside, keep the inside the same, times the derivative of the inside, and that's my chain rule. So now h prime of 2 is going to be f prime of g of 2 times g prime of 2. So f prime of g of 2. So what's g of 2 going to be? So that's 3 times g prime of 2, which is 3/2. Now I'm going to go to my chart. I'm going to find f prime of 3, which is a negative 1 times 3/2, which gives me a negative 3/2 as my slope. So my tangent line is going to be a y minus 3 equals a negative 3 over 2 x minus 2, which would be a y equals a negative 3 halves x minus 2 plus 3. And feel free to distribute that if you like. I actually do think if you distribute it, it works out very nicely. But to save time, I'm going to leave it as point slope form. Okay, so let me fix my pen here so I can circle my answer. This is my tangent line. So let's do it one more time. So again, I want my point. I want my slope, right? So my point is going to be a 1 comma, right? Because I want the slope of the tangent line at 1. So j of 1 is going to equal g of f of 1. No derivative needed for that. So f of 1 is 5. So that gives me g of 5. And then what's g of 5? So that's going to be 6. So my point is 1 comma 6. So now I want to do my derivative. J prime of 1 equals g prime of, let's start with x first. G prime of f of x times f prime of x. So then j prime of 1 is going to be g prime of f of 1 times f prime of 1. Now we said before f of 1 was 5, so my slope is going to be g prime of 5 times f prime of 1. What's f prime of 1? Negative 1. So then g prime of 5 is a negative 1/2 times a negative 1, which would be a positive 1/2. So slope of my tangent line is a y minus 6 equals a 1/2 x minus 1, or in this case, a y equals 1/2 x minus 1 plus 6. And this is my tangent line. Okay? I'm going to keep going. Example 11. I give you two functions, f of x and g of x. At what x values of x do the graphs f and g have parallel tangents? So reminder, parallel means same slope. So I want to know when those two tangents have the same slope. So what I'm going to do is I'm going to find f prime of x, which would be a 2. E to a power is still e to the same power, but I have to take the derivative of that power, which is 3. So I'm going to write this actually as a 6e to the 3x. And then g prime of x would be a 15x squared. So if I want to know when they have the same slope, I'm going to take a 6e to the 3x, and I'm going to set that equal to a 15x squared. And I want to know when those are the same. Now, if you notice, I put a little disclaimer here. A calculator is required. The way that I would solve this is in my calculator, I would let y1 be a 6e to the 3x, and I would let y2 be a 15x squared, and then I would find the intersection between the two of those. Okay, so I'm going to find the intersection. All right, so if you find that intersection, now let me pull up my calculator. So let's do this. Oops, sorry guys. So if I were to, in my y1, let me open up the right calculator. There we go. All right, so this should be the same as you. So I am going to put in my y1 a 6 e to the, I have a 36 in there, sorry. 6e to the 3x power, and then in y2, I have a 15x squared. Oops, let's get this right. X squared. I'm going to graph those. So you get a look at what this graph looks like. There we go, okay? And I want to calculate the intersection. So number 5 of those two things. And the intersection I get is at 0.3655. Always at least 3 decimal places, guys. You could truncate if need be, 2.004. But it didn't really ask for the y value. It says that what x values. So my answer to this question is when x equals 0.3655. Okay? So let's keep going. So number 12, let f be a function given by f of x equals 5e to the 3x cubed. For what positive a is the slope of the tangent to the graph of f equal to 6. So I want to know the point of where the slope is going to be 6. So that means I want to know ultimately when is f prime of x going to equal 6. I'm going to use my calculator for this as well. I'm going to take the derivative. So the derivative of f of x is still going to be 5e to the same power, 3x cubed. But you still have to take the derivative of that power, which is going to be a 9x squared. And I want to know when that's 6. So let's clean this up a little bit. A 45x squared e to the 3x cubed. And I want to know when that's 6. So I'm going to go to my y equals. I'm going to kind of cheat here. Calculator is required. But the way that I do this on my calculator is I'm going to put the left side of the equation, 45x squared times e to the 3x to the third power, right? Make sure we type in everything right there. And then y2, I'm just going to type 6, right? And again, I'm just going to find where those two things are equal or where they intersect. And let's see what we get here. Now notice the question says for what positive a value, right? So if you notice, there's actually 3 points of intersection here, but the question only wanted for when it was positive. So if I find the intersection, okay, for that positive value is going to be at 0.3435 for my answer, okay? Now, if I wanted to know the y value of that, I could find the output of that function. So to get the full coordinate, okay, I could actually, I'm going to go to my home screen on my calculator, and I'm just going to type in 5 times e to the 3 times 0.3435 to the third power, right? So that will give me my y value or approximate value of my y. So the coordinate where that happens is 0.3435 comma 5.646, okay? And that is my answer. Now, if you wanted to leave it exact and just plug in the x value and circle it, I would be okay with that too, but we can find the output. Last problem. I know it's been a long video, okay? Last problem. Let's make my screen full screen here, okay? Determine if the following function is differentiable. So remember, differentiable, it's got to be continuous, which means the limit as x approaches 0 from the left of f of x has to equal the limit as x approaches 0 from the right of f of x, which has to equal f of 0, right? The other thing is, the other piece to the puzzle is the slope from the left. So the limit as x approaches 0 from the left of f prime of x has to equal the limit as x approaches 0 from the right of f prime of x. Oops. We need to do these two things. We need to show that these two things are true. If either of these fails, then it's not differentiable for that function. So the blue part doesn't really require any derivatives. I'm going to plug 0 in from the left, so I'd get sine of 0. And 0 in from the right would be the second half, which would be still 0, because 0 times e to the 0, right? So I'd get something like 0 times 1, right? Sine of 0 is 0 equals 0. So that's true. And f of 0 is also 0. So it is continuous. All right. But now I want to take the derivatives, right? I want to check the derivatives from the left and the right. So let's take the derivatives. F prime is going to be a cosine of x cubed plus x squared times the chain rule of a 3x squared plus 2x. And the derivative of the other, now I have to do a product rule for the second piece. So the derivative of the first is 1. Leave the second the same, so e to the x squared, plus, now keep the first the same, derivative of the second is still e to the x squared, but chain rule gives me an extra 2x. And I'm going to check 0 from the left, which would be the first half. Okay, now if I plug in 0 from the left, I get a cosine of 0 times, if I plug in 0 for the inside of that expression, that's 0, which equals, if I plug in 0 from the right, I'm going to get a 1 times e to the 0, which is 1, plus 0 times e to the 0 times 0. So cosine of 0 is 1 times 0. This is going to be 1 times 1, which is 1 plus 0. So I get 0 equals 1. That is not true. Therefore, this function is not differentiable at 0, because the slope from the left does not equal the slope from the right. Okay? So that concludes the video. I know it's a long video. The purpose of this video is one, chain rule. I tried to apply it in all the different derivatives that we know, as well as function notation. And lastly, I wanted to pair it with the new ideas. So take a time, rewind, rewatch. This is a very important topic. And if you have any questions, please let me know.